Log on, tune in, find out. Another good idea from Cambridge.
And coherent systems on nodal types.
Well, coherent systems and bilinear loci on smooth curves have been studied for several years now. They need no introduction, I think. For small values of genera, that is for the smallest values 0 and 1, they were studied by Newstead and Langer. The purpose of this talk mainly is to generalize these results to nodal curves. So, for genus 0, any integral curve of arithmetic genus 0 is a P1, so there is nothing to do there. We have already done it more or less. For the genus 1, the curve is either an elliptic curve, which is a smooth curve, or it's a rational Weierstrass rational cubic curve with one node or one cusp. So, most of the talk we shall assume that the curve is a rational curve with one node. Before we go to restrict ourselves to this kind of curve, we will first recall some results and definitions on coherent systems on nodal curves. So, let us start with fixing notation. Can it be seen? All these. Oh, yeah, okay. So, for a torsion-free sheaf E, we have the usual notations RE the rank of E, D the degree of E, and mu E the usual slope of E, that is the degree of E divided by rank of E. Then we have this Crookes home EF, that is the global homomorphisms from E to F, and the sheaf home EF, the sheaf of homomorphisms from E to F, different notations. Similarly, for X groups and X sheaves. So, at a node Y, let M denote the local ring. So, A is the local ring and M is the maximal ideal at Y. Then the stock of E, I mean the stock and not the fiber. The stock of E is of the form AE A plus BEM, where A means A direct sum A E times. Similarly, for BEM, and both A and B are non-negative integers, and their sum is equal to rank of E. So, the fiber of the such a sheaf will be a vector space of dimension AE plus twice B. Then we have the usual definition of coherent sheaf. A coherent sheaf of type NDK on a nodal curve X is a pair EV, where E is a torsion-free sheaf of rank n, degree D, and V contained in H naught E is a subspace of dimension K. So, given a coherent system, we can talk of subsystems. So, a subsystem EV, probably most of you know, E prime V prime contained in EV is a pair such that E prime is contained in E and V prime is contained in H naught of E prime intersection V. We call it proper if the pair EV is not equal to E prime V prime. Either E could be prime or V could be V prime, that is possible. We fix a real number alpha, and for alpha in R, we define a alpha slope mu E, mu alpha EV as usual slope degree of E upon rank of E plus alpha times dimension of E upon rank of E, These are the same definitions more or less as we do in smooth case. And a coherent system EV is called alpha stable if for every subsystem, proper subsystem E prime V prime, we have this mu alpha of EV strictly less than mu alpha of E prime V prime is strictly less than mu alpha of EV. And semi-stability is defined as usual by non-strict inequalities. So, the moduli spaces of coherent systems, in fact, for not only for nodal curves, but for any scheme of pure dimension 1, they were constructed by Pluton-Nisted and Alatzel-King. So, I am just quoting their theorem. There is a projective coarse moduli space G alpha in decay of alpha semi-stable coherent systems. Sorry, it should be G tilde alpha in decay. The open subscheme G alpha in decay of this projective scheme, which consists of alpha stable coherent systems, is a coarse moduli space for alpha stable coherent systems. We also have an open subset there, G prime alpha in decay. The prime usually denotes that the underlying sheaf is locally free. Normally, G prime alpha in decay will have better properties than the G alpha in decay. That is why we need this to prove various things actually. So, we have this stability conditions. Associated to any billinear locus or model of coherent sheaf. There is always some expected dimension beta in decay. In our case, genus 1 case, this beta indicates as k into d minus k plus 1. From general theory, it follows that the Zariski tangent space to the moduli space of coherent systems at any point EV is isomorphic to the first x1 group, x1 of EV. So, you can define morphisms of coherent systems. Morphism from E1 V1 to E2 V2 will be a morphism from E1 to E2, which such that the corresponding map on H0 maps V1 to V2, and then you have the associated derived functors x star. The x1 gives you the Zariski tangent space as usual. If x2 of EV is 0, then the moduli space of alpha stable coherent systems is smooth at EV, and it has dimension x1 of EV. A very useful tool in determining the smoothness is a Petri map. So, the Petri map of a coherent system EV on X is the map H from V tensor H0 of E star. This is in case genus is 1, otherwise it will be V tensor H0 of E star tensor K. K is the dualizing sheaf to x1 of E star. Star denotes the dual, and this is dual to the natural map x1 of E to V star tensor H1 of E. If E is locally free, then this is the usual Petri map that we are familiar with. So, it is the map from V tensor H0 of E star to H0 of ND given by multiplication of sections. But in general, for non-locally free sheaves, these two maps are different. So, we have some general results now. the dimension of the irreducible component S prime of G alpha in decay passing through EV satisfies dimension of x1 of EV is greater than equal to the dimension of S prime, and which is greater than equal to beta in decay minus B square. B was the integer which was obtained using the stock of the sheaf. If the usually for smooth curves, if Petri map is injective, then you get that the moduli space is smooth of dimension beta in decay at that point. This is not quite true in non-smooth case. So, if the Petri map is injective and E is locally free, then only you have the moduli space is smooth at that point, and then it has the correct dimension beta in decay. Normally what happens is that even if the Petri map is injective, all that you get is x2 of EV is x2 of E, which is non-zero. In fact, it is equal to 2 times E square. So, you do not have smoothness. And if the Petri map is injective, then dimension of x1 of EV is beta in decay plus B square. It also depends on the local structure. To study coherent systems on a curve of genus 1, it is very essential that you have a good knowledge of indecomposable torsion free sheaves on X. So, next we will try to understand the indecomposable torsion free sheaves on a Weierstrass nodal curve. Whether the curve is smooth or non-smooth, there are some bundles which are always there. They are the so called Atiyah bundles. So, I will just recall the definition. The Atiyah bundle F1 is just the trivial rank 1 bundle, that is corresponding to the structure sheaf, and for r greater than equal to 2, it is defined inductively. So, by the sequence 0 to Fr minus 1 to Fr to O to 0. This is indecomposable semi-stable bundle, but the thing is that on a smooth curve, any indecomposable bundle is semi-stable. This is not true on nodal curves. So, there are indecomposable bundles which are not semi-stable, and we have a characterization of such bundles or sheaves more generally. Let E denote an indecomposable non-semi-stable torsion free sheaf. If 0 equal to E naught contain E1 contain ER, which is E, is the Haldane-Nursivan filtration of E, then all the EIs and quotients E mod EI, they are not locally free for all I less than R. So, your ER could be vector bundle, but if it is not semi-stable, then all the things in the Haldane-Nursivan filtrations are not locally free except itself. Apart from this characterization, there are also other ones actually, and Gulban and others had constructed indecomposable vector bundles and also indecomposable torsion free sheaves on nodal curves using other methods. We need them, so we just recall quickly what they do. So, these are constructed from cycles of P1s. We denote by En the cycle of P1s with n components. We have an ethyl covering from En to X. If Ei prime is one component, which is a P1, then restriction of this map En to X to Ei prime to X should be the normalization of x, the normalization map. For any integer, any sequence of integers d bar equal to d1 to dn, and any lambda in k star, we define a certain line bundles, they define some line bundles LD lambda. I won't go into the definitions, which combine some things, but the point is that if you take the direct image of this LD lambda, that is an indecomposable vector bundle, and you could tensor it with all Atiyah bundles, and we call this bundle B MD lambda, which is direct image of LD lambda tensor with Fm, and these if you take D such that the sequence d1 due to dn is not a periodic sequence, that is there is no subsequence of d1 due to dn such that d1 due to dn is just a repetition of that sequence, then in that case all these BMD lambda are indecomposable vector bundles, and these are the only indecomposable vector bundles on the nodal graph. So, this is very useful. So, we use this idea and we construct on x regular class x, x regular class En, first a family of line bundles on En parameterized by x regular, and then we just copy the L construction, we take direct image of this family and tensor with pullback of Fm. So, we get a family Bm d bar of vector bundles on x parameterized by x regular. This family will be very useful later. So, we have all indecomposable vector bundles, but we still have to get the indecomposable torsion free sheaves which are not locally free. So, this is construction for that. Now, we do not choose the cycle of P1s, what we use is a chain of P1s. So, you take En plus 1 cycle of n plus 1 P1s, remove one of the P1s. So, that gives you a chain of P1s, we call it In, it has n plus 1 n components. We just restrict the map from En plus 1 to x to In to x and call it Pn. It is well known that the Picard group of In is just Z power n. So, any line bundle on In is determined by its restriction to each of the pivots. So, let di be the degree of L restrict to Ei prime. Then the indecomposable non-locally free torsion free sheaves on x of rank n and degree 1 plus sigma di are given simply by taking direct image of the LD bar. LD bar is the line bundle which has degree d1 d2 dn on the components. We will use these things to show reducibility of model space and also some other purposes. Also, these descriptions of indecomposable torsion free sheaves and vector bundles, we use them to show that the only indecomposable torsion free sheaf which has non-trivial H naught is the Atiyah bundle, and Atiyah bundle has just one dimensional space of sections. So, now armed with all this information, I think we can go to the Moduli spaces now. So, we have these integers n and d both are assumed to be positive, but k 0 case is of course very easy. For k equal to 0, this G alpha n d 0 is just the model space of torsion Clesius. It is known that this space is isomorphic to X because it is genus 1 curve, and it is isomorphic to X in the coprime case, and in non coprime case, if you take H to be the greatest common divisor of n and d, then the model space of torsion Clesius of rank n and degree d is just H symmetric power of X. So, we can now assume that k is also greater than 0. The simplest case is of course the case of line bundles or rank 1 torsion Clesius. So, in this case there is no semi-stability condition, every coherent system is alpha stable. So, let J bar be the compactified Jacobian of X, that is the model space of torsion Clesius of rank 1 degree d. On this J bar cross X we have a universal family, the Poincare family. It is not a vector bundle, it is a sheaf P on J bar cross X, and since we have assumed degree greater than 0, H1 of any torsion Clesius H1 of any rank 1 torsion Clesius is 0. So, the direct image of P on J bar is a vector bundle actually, that is the Picard bundle. It has rank d, and fiber of it over each point of J bar is just, say L is the, it corresponds to L, then the fiber is just H dot of L. So, we can just construct Grassmannian bundle over this Picard bundle associated to this Picard bundle, that is the bundle over J bar, such that its fibers are Grassmannian of R k dimensions of spaces of d dimensional vector space. So, that will be our G alpha n d k in this case. Now, how the curve X is rational, and this bundle is Zariski locally trivial Grassmannian bundle on it. Therefore, the G alpha n d k is rational in this case. If you consider only the, okay, we will go to that later. The curve X is also semi-normal, it is not, and there is a theorem of Traverso that the product of a normal variety with a semi-normal variety is a semi-normal variety. So, it follows that G alpha n d k is also semi-normal, and if you restrict to G prime alpha n d k, which means that E is actually locally free, the line bundle is locally free. So, we have line bundles only, then they correspond to X prime, the non-single set of X, which is a smooth variety, and therefore, G prime alpha n d k will be actually non-singular. So, it is much better than the G alpha n d k. So, this much for rank 1. So, let us go to higher ranks now. So, first of all we consider the necessary conditions for non-emptiness. I think that is the first thing, because we have to know when they are non-empty, at least first when they are empty. So, the theorem is that G alpha n d k is empty if either d is less than k, and if k is equal to d, then the condition is they are empty if the greatest common divisor of n and d is not 1, that is n and d are not co-prime. The second case, k equal to d, is somewhat easy to handle. First of all, k equal to d means that V is equal to H naught of E, because canonical bundle is trivial, H1 is 0, so H naught is just D. And in the non-coprime case, there are no stable bundles on X. So it is easy to see that any coherent system is a direct sum of subsystems, at least two of them, and hence it cannot be stable. So there are no stable things there. The proof in the other case is somewhat long, it is not very easy. So first of all, you use alpha stability of coherent systems to show that if you have any quotient q of E, if it is stable and not equal to the trivial line bundle, then it must have positive degree. If it is semi-stable, it has non-negative degree, and if it has no sections, then also it has positive degree. So all this can be deduced from alpha stability. Then we use our characterization of non-semi-stable indecomposable bundles to show that any indecomposable direct sum on f of E has positive degree. And then we use our computations of H naught of indecomposable sheaves to show that H naught of E star is 0. Once you have H naught of E star 0, then by Searle duality H1 of E is 0, which means H naught of E is D by Riemann-Roch, and that means D is greater than or equal to k. So for D less than k, you cannot have any alpha stable coherent systems. That is the idea of proof. Of course, next natural question to ask is whether these model spaces are irreducible. If they are irreducible, what is the dimension? Whether they are of expected dimension or not. One would also like to know about singular set of the model spaces. So we investigate these things now. If G alpha indica is non-empty, then it is irreducible and it is of correct dimension, beta indica. Moreover, G prime indica, that is the one corresponding to E locally free, that is non-empty if and only if G alpha indica is non-empty. So there is always a coherent system with underlying sheaf locally free whenever the model space is non-empty. And the singular set is as one should expect, it is G alpha indica minus G prime alpha indica. So if you take the model space of torsion free sheaves on nodal curves, then it is not even normal. But the subset corresponding to vector bundles, that is a normal subset. This kind of thing is reflected here also. So I will just briefly sketch the idea of this proof. This proof is very long actually, runs several pages, and this is the place where you use all these construction of indecomposable torsion free sheaves families and things like that. So, we recall that we had constructed this family BMD of vector bundles on X parameterized by X regular. So, now we take BMIDI, we are just attaching a suffix on a X regular across X, the family which contains all indecomposable vector bundles EI on X with fixed MI and DI bar. Let UI be the open subset of X regular corresponding to those EIs for which H naught of EI is degree of EI. That is the same thing as H1 of EI is 0. Then we fix M delta, which is a H tuple of integers M1, M2, Mh, that is M, and delta is H tuple of D1, D bar, D2 bar, DH bar, where H is the GCD of N and D. Then for fixed M delta, we will have this various product of various UIs, and that will parameterize a family of vector bundles E equal to direct sum EI with EI indecomposable. There will be the open subset of this. So, you have this product UIs, you can construct on them a Grassmannian bundle as we did in the rank 1 case, which has fibers Grassmannian of k dimensional subspaces of d dimensional vector space. And inside this, so this will be essentially parameterizing various coherent systems that we want. Inside this, we take a open subset U, which corresponds to stable alpha stable coherent systems, and by universal property of Moduli space, there will be a mapping phi. I do not know whether I have written it, from this set U to G alpha indicator. So, we want to estimate now what is the image of this set. So, we have this mapping phi from G alpha in decay U to G alpha in decay. Let A be the minimum of dimensions of automorphism of E. Certainly, automorphisms of E are contained in the fiber of this map phi. So, you take minimum of dimensions of E, where minimum is taken over all E such that EV belong to this U open set. Then the dimension of phi U is H plus dimension of GRKD minus A plus 1. This needs some computation, but that works out to be equal to beta in decay plus H minus A. H is the GCD of N and D, and since A is always greater than or equal to H is the minimum possible actually, and the automorphism group is H, has dimension H if and only if E is of the form direct sum EI, where EI are all indecomposable and non-isomorphic. So, the dimension is of this set is always less than or equal to beta in decay, and it is equal to beta in decay if and only if E is of that particular form. So, we denote by UCS the open subset of U corresponding to E such that all the components EIs are stable. Our proof is still halfway. since we have seen that the dimension of phi u is correct dimension only in case E is of the form direct sum EI, where EI's are all indecomposable and stable and non-isomorphic. So, we construct a family first with this kind of E. So, you have the moduli space U n by h, all of them will have rank n by h and degree d by h. So, you consider the moduli space U n by h d by h, the moduli space of stable torsion free shoes of rank n by h and degree d by h. This is known to be isomorphic to x, because now d by h and n by h are co-prime. You take the product of all these x things and then construct a Grassmannian bundle over that. So, I am calling that Grassmannian bundle GRXH, and let W be the subset of this Grassmannian bundle corresponding to alpha stable coherent systems. So, this will be our major open subsets out of, and by what we the dimension computations that we did, there will be a mapping from this open from this W to G alpha in decay, and the dimension of the image will be exactly beta in decay. So, if we take closure of this set, that will be certainly be an irreducible component of correct dimension. Of course, you could have the other indecomposable components, so you have to rule out that possibility. So, recall that if you have U which is dependent on m and delta, um delta, which gives an irreducible component of G alpha in decay, then the general EV in that U had to be a stable bundle, had to be a bundle of this form E equal to direct sum EI, which belong each EI belong to U n by h d by h and so on. So, all images I mean the open sets of all such U will map into this component G alpha, which means that no component of G alpha in decay minus G prime alpha in decay, which is outside G, can have dimension beta in decay. Now, what remains to check is that we do not have a component consisting of only non-locally free torsion free shoes. In general, in moduli spaces of torsion free shoes on singular curves, there could be components which consist only of non-locally free shoes and they have higher dimension actually. So, such a thing does not happen, that is what you have to check. For that, what comes useful is our description of indecomposable torsion free sheaves which are not locally free, construction using this not cycle, but chains of events, we had done this construction. So, using that construction as we did in the locally free case, we can check that the components that we can get from non-locally free sheaves, they are also of dimension strictly less than beta in decay, which shows that there is only one component, and that is what we called GV in decay. So, we have our G alpha in decay irreducible. Now, let us go to smoothness. We had already checked while proving irreducibility in that it is not a P star is 0 if EV is alpha stable. So, almost trivially it follows that this Petri map is injective, and therefore, if E is locally free, then EV is a smooth point of G alpha in decay. which means that G prime alpha in decay is non-singular. Moreover, the dimension at the smooth point is x1 of EV, which is easily computable to be beta in decay. But if you have a point corresponding to non-locally free sheet, then your x1 of EV, if you remember, had dimension beta in decay plus B square. So, it does not have correct dimension, which means that it cannot be a smooth point. So, the singular set is precisely G alpha in decay minus G prime alpha in decay, the subset corresponding to non-locally free shears. Okay, we had conditions for non-emptiness, so they were necessary conditions, but they do not necessarily means that for those values, allowable values, the moduli spaces still exist. So, we have to show the check the non-emptiness of moduli spaces. So, we assume all necessary conditions, that is d is greater than k, and if d is k, then the n and d are co-prime. Then the result is that define I in decay to be the set of alphas such that G alpha in decay is non-empty. This can be shown to be a open interval. The proof is more or less same as in the smooth case. And G alpha in decay is non-empty for small values of alpha, and values of alpha sufficiently near to 0. If k is less than n, then it is well known that G alpha in decay is empty for alpha greater than d upon n minus k. This you can prove in any case, smooth non-smooth case, proof is same. And also there is a coherent system of time in decay, which is alpha stable for all alpha in that interval where it is non-empty. Moreover, if k is n equal to, then the G alpha in decay is non-empty for arbitrarily large values of alpha. All these things work more or less same way as in the smooth case. There is nothing extra to be done here, because the proofs essentially involved only slope and usual semi-stability condition computation. So, now we take the last case, k greater than equal to n. If the curve is smooth, then it is known that in this case also G alpha in decay is non-empty for arbitrarily large values of alpha. We do not know if this is true in our case, we have only partial results. So, if you have low ranks, that is rank is less than equal to 3, then you can show that G alpha in decay is non-empty for arbitrarily large alpha. So, there are two other cases also, namely k equal to n plus 1 any rank and k equal to n plus 2. K equal to n plus 1, the proof is essentially due to Bellico, and the proof can be pushed further to k equal to n plus 2, but it can't go beyond that. It's impossible. It's very clearly seen that for k greater than equal to n plus 3, it's not going to work. So, for k n less than equal to 2, that is for small ranks, what does one do? I mean, for example, in smooth case what one does. So, you always have this for small values of alpha, that G naught alpha indicate, that is non-empty. So, you can use flips and see that when you use flips, to get to the for larger values of alpha, you have to add some subset, and also some subset of G naught gets subtracted. And when you do this, you still get something non-empty. So, you need to do some dimension computations, and the computation of these things needs considering torsion-free subsheaves also. And the very fact that x1 for torsion-free sheaves is much bigger than h1 makes it impossible. All the computations go haywire, except in case n equal to 3, where up to 3, where the subsheaves are very low rank 1 or 2, and then I can sort of manage that the subsheaves very old subsets of much lower dimension than the addition that you get from x1 more in addition to h1. So, finally, it is okay in less n equal to 3. I do not know what to do with higher ranks. So, for these values k greater than equal to n and n greater than equal to 3 and k greater than equal to n plus 3, the problem is still open. Okay. So, now let us see what other properties these spaces have. We know irreducibility, we know something about its non-singularity. So, let us see some examples now where more things are known, and also some more general properties. First of all, the birational type of G alpha and k is independent of alpha belong to I, this interval, and in case x is nodal, G alpha and k are actually unirational. This is not true in the smooth case. This rationality and unirationality are special because our curve is rational. If k is d and n and dn co-prime, then you get then you can show that there are no critical values, that is the moduli space does not change as you vary alpha, and then G naught n d d and GL n d d, that is the moduli space for large values of alpha, both of them are isomorphic to actually x. And in particular they are rational and semi-normal. In case n and d are co-prime, then G naught n k is just a projective bundle over x, and in case x is nodal, again by the argument in the rank 1 case, one sees that this moduli space is again rational and semi-normal. Moreover, the subset G prime and k will be non-singular. And in this particular case, that is co-prime case, G alpha and k is rational for all values of alpha. There are other still smaller examples. So, for any n d equal to 2 and k equal to 1, this G naught n 2 1, it is again same as GL n 2 1, and it is a P1 bundle over x. So, we have these very explicit descriptions In one case it was the curve itself, here it's P1 by lower x, and all of this again in this case also these varieties are rational and semi-normal for nodal case. In case GCD of n minus k and d is 1, k is less than n and k is less than equal to d, then G alpha and k is again rational for all alphas. Moreover, the GL and dk, the moduli space for larger values of alpha, that's even semi-normal. So most of these varieties seem to have properties like rationality and semi-normality shared from the curve. Maybe I'll stop here. Now 5 minutes more.
Any questions?
So how do the moduli, these moduli of systems for the nodal curves, can they be seen as a degeneration for as compared to what happens in the smooth curve? So do they all fit into one big family, you think?
I don't think it's even done for Brill nodal case.
I don't know.
Yeah, it's not done as far as I know. Yeah, of course, moduli of torsion ratios do fit in a family. So possibly these also. But I haven't tried it yet.
Any more questions? Okay, so shall we thank Usha again?